I like to start this lesson in my classroom by asking students what they think their velocity is at that moment in the classroom. And the most common answer I get, which is probably the most sensible answer you can give, is that their velocity is 0. They tend to think because they are sitting in a desk, in a chair, not moving across the floor one way or the other, it's reasonable to have to say that they have a velocity of 0. And certainly that's a reasonable answer. But occasionally a student gives an answer like, well, I'm on planet Earth and Earth is hurtling through space, or Earth is spinning in a circle. So actually my velocity is really fast. And this kind of sparks a bit of discussion. And then we get down to thinking, okay, well, which of these answers is correct? From the perspective of the ground, you're not moving because you're staying in the same place on the ground. But from the perspective of someone floating around in space who sees Earth zooming past them, you're moving really fast. And if you zoom out even further, Earth is part of the Milky Way galaxy, which is hurtling through space itself. So the idea is, depending on where your velocity is measured from, it can have very different values. And we often, are tempted to ask, well, which one is correct? And the idea with this lesson is to push past that idea of one being correct and to get to a point where we can say all of those velocities are valid, and no one's any better than any other. So, to the question, what's your velocity right now? It depends on the perspective. And by perspective, I mean where it's measured from. We would say the velocity is 0 if you're sitting at a table. If the velocity is measured from the ground, but if we're floating in space and measuring your velocity as you sit on planet Earth and hurtles past, we're going to get a really, really big number for that velocity. I won't get into what the number is. We can talk about that in a later unit. So the idea is not just your velocity, but the velocity of any object is relative. Meaning the number you would get, or the amount you would get, it's relative to where you measure it from. So in some situations, it's not really obvious where a velocity is being observed from. in which case we're going to need to say it explicitly. So rather than saying my velocity is 0, we'll say my velocity is 0 if measured from the ground. So that's a habit we're going to have to start getting into. Up till now, probably in your physics learning, you've never had to think about this before. You've always just stated a velocity as, a magnitude and a direction, and that's what it is. And that's probably because up till now, almost every velocity you've ever thought about has been measured relative to the ground. And we're going to change that a bit in today's lesson. And let's start with a simple example. So there's a student, and if they are in still water, so an example of still water would be like if they're on a lake, they can paddle a canoe at 3 meters per second. So this is what they are capable of. The act of paddling a canoe is you put your paddle in the water, you push against the water, and when you do that, you cause the boat to move relative to the water. That's what paddling does. It makes your boat move relative to the water. So the boat and the water are doing different things. And they're different by 3 meters per second. So this student then paddles down a river that flows at 7 meters per second. What's their velocity relative to the shore? Well, if you look at this question, you think, okay, if they weren't paddling at all and they were just floating with the river, they'd be doing 7 with the river. But if they're pointing down the river and then they start to paddle, which means they are able to do an extra 3 compared to what the water is. They're pushing against the water so that they do 3 more than it. Then they're going to have a velocity from the perspective of the shore of 7, which is what they'd get for free from just floating in the river, plus 3, which is how much extra they get when they push against the water with their paddle, is 10 meters per second. Okay, that seems fairly intuitive. If they then turn their boat around, decide they don't like where this river is heading, and they now paddle up the river, what would someone on the shore see them doing? Well, again, there's the 7 meters per second that they would get for free by just being in the river and floating with it. But as soon as they put their paddle in the water to start pushing one way or another, they do something in addition to that 7. And in this case, they're pushing sort of against the flow of the river. So the extra 3 meters per second they get from paddling is sort of going against this 7 that they have from the river. So we're going to subtract it. Okay. So most people can kind of answer those questions without thinking too hard about it. Now there's an equation that actually governs how this stuff all works. And we just use this equation, only we used it without ever having learned it. We used it because it sort of makes intuitive sense in our heads. The equation is this. The velocity of the boat as viewed from the river plus the velocity of the river as viewed from the ground equals the velocity of the boat as viewed from the ground. And because velocity is a vector, direction is important here, right? When I changed the direction I was paddling, I had to change something in my equation. So direction is important when we're talking about velocity, so all of these guys need vector hats. So that's kind of what we just did. Velocity of the boat with respect to river. So that's how fast the boat would be going if you can imagine yourself being the river, being part of the river. What would you see the boat doing? That's what the boat is doing in addition to what the river is doing. So that's the 3 meters per second here. And that 3 can be positive if we're going with the river, or negative if we're going against the river. The velocity of the river with respect to the ground, that's my 7. That's how fast the river's going. And then the velocity of the boat with respect to the ground, that's was these numbers here that we were trying to find. The velocity relative to the shore. So let's unpack this equation a little bit more. So there's a few terms here. Let's start with kind of some of the easy ones. This middle term, velocity of river with respect to ground, this is usually pretty straightforward. This is sort of what the river's doing. So what the river's doing. It's what the river's doing relative to the ground. But again, we spend almost all of our lives on the ground, measuring things from the ground. So we don't even really think about the fact that we're on the ground anymore. It's just a given. So most people just think of this as what the river is doing. Similarly, because this term over here is also measured with respect to the ground, people have a decent intuitive understanding of what this means. This is what the boat is actually doing. I say the word actually, I'll put this in quotes because this is how people like to think of this term. It's sort of, like I said, because we spend our lives on the ground, this is what we think of as the boat's motion, this term here. Now, this third term, or this first one, over on the left, is the one that's a bit trickier, because this one measures the boat's velocity from the perspective of the river. And most of us don't spend a lot of time stuck to a river. So imagine you are in sort of a floaty tube, and you've stuck yourself in the river. Because this floaty tube doesn't have a motor or paddles or anything, you are just at the mercy of the current. You do exactly whatever the river's doing. The river's going 7 meters per second, you go 7 meters per second. If the river stops, you stop. So this whole term here is basically what you would see if you were in that floaty tube, being part of the river, looking at the boat. So because this term is the less easy one to sort of sometimes figure out, there's a few key words and key phrases I want you to watch out for in problems that give you a hint we're talking about this term. One of them is the phrase "in still water." We saw that phrase in the example we did already. It started with that phrase. When you see that, it means we're talking about what the boat is able to do in addition to or compared to the river or the water that it's in. The other phrase I want you to watch out for is the phrase heading. Heading means sort of the direction something is pointing or the direction something is aiming. So, for example, the boat in our problem sometimes was aiming downriver and sometimes was aiming upriver. So we are heading in one situation was positive, and another situation it was negative. And this in still water phrase up here gave us a speed of 3, and that showed up here and here. So one way to think about this is if you see the in still water phrase, it's telling you the magnitude of this term. And if you see the phrase heading, it's telling you the direction of that term. And that's exactly what we see up here. There's a magnitude, and there's a direction. And then this little symbol right here, one I've mentioned a few times, that means with respect to, or as viewed from, or compared to. This tells us where this velocity is being measured from. Okay, so this was a pretty simple example to start with. You might be thinking, well, why do we need all this big fancy formula with all these vector hats and new symbols and new jargon to answer a question that I could do in my head? And as I kind of often like to do when we're introducing a new topic, I like to start with a simple question that you can probably do in your head, show you a method that also gives the same answer to kind of convince you that the method works and that the method's legit. And then we come to trust the method so we can use it for more difficult problems. So let's look at another problem. And this one isn't actually much more difficult. You could maybe still do this one in your head, but let's look at it nonetheless. A bullet whizzes past your head at 500 meters per second north, fired from a car which soon whizzes past you at 50 meters per second north. How fast was the bullet going as viewed from the car? First thing I notice here is there is no boat and no river in this question. And some people, when they look at this formula up here, they actually don't use the words boat and river. They call it like object 1 and object 2. So boat is object 1, river is object 2, ground is object 3. I like to think of them as the boat, the river, and the ground because that gives me a bit more of a visual understanding of what's going on when we use this equation. But it works even if it's not a boat and a river and a ground. It works for any 3 objects that are all moving relative to each other. So I like to stick with the boat and river analogy, and I bake that into the formula. But in this question, we're going to have to think, okay, what thing is kind of like the boat? What thing is kind of like the river? And what thing is kind of like the ground? Well, the way I like to kind of think about this is that the river flows over the ground and carries the boat on top of it. The boat gets whatever the river's doing for free, and then it can choose to do a little extra something in addition to that. So if I think of it that way, the river flows over the ground and carries the boat. What is like the river, what's like the boat, and what's like the ground in this question? Well, I would say the car drives over the ground, and being carried in the car is this bullet, just like the boat that's being carried by the river. And just like the boat can do something a little more or a little less than what the river's doing, the bullet depending on which way it's fired, can do something a little more or a little less than what the car is doing. So I think in this question, it's fair to say that the boat is the bullet. The river is the car. And we'll say that you are on the ground. I think that's a fair assumption we can make in this question. So the ground is where you are, and that's the ground. The ground is the ground. Okay. So now we have to look at kind of what's given to us in the question. So there's 3 velocities we might be interested in. Velocity of bullet with respect to river, or with respect to car. Velocity of car with respect to ground. And velocity of bullet with respect to ground. So as I read through the problem, what can I figure out here? A bullet whizzes past your head, so you're on the ground, at 500 meters per second north. So that's going to be the velocity of the bullet as viewed from you on the ground. Then the car whizzes past you. So this is going to be a velocity of the car as measured by you, or with respect to the ground, 50 meters per second north. And then we want to know how fast was the bullet going as viewed from the car. So that's this guy right there. Well, we can write our equation out again. Velocity of boat with respect to river, so bullet with respect to car, plus velocity of a river with respect to ground, so in this case, velocity of car with respect to ground, equals velocity of boat with respect to ground, or bullet with respect to ground. Some people kind of like to think of these as like fractions that are kind of canceling out. So B over C, and then you have C over G, and these two C's sort of cancel each other out. So you have B on the top and G on the bottom, and that's how you get this B and this G here. That's not really what we're doing. Those aren't actually fractions, and we're not multiplying them. But if that helps you kind of remember the order that, that these terms go in, then feel free to use that as like a little mnemonic. Okay, so plugging numbers in, I say velocity of bullet to car. That I do not know. That is the thing I'm looking for. Plus velocity of car to ground. That is 50 north. And since this is a 1D problem, everything's in the north-south direction, I can just communicate this north part by just saying it's positive direction. So this guy is going to be positive 50. equals velocity of bullet to ground, and that is 500 north, so positive 500. So then if I rearrange and solve for velocity of bullet with respect to car, I get 500 minus 50, or positive 450 meters per second. Okay, again, this question is one that you likely could have done in your head once you kind of had it all sorted out. The idea here is to show you this formula, show you this approach with figuring out what's the boat, what's the river, what's the ground. Using this idea of writing down the things we know and figuring out what the unknown is. And then going to the formula and plugging in our unknowns, including their directions, and solving. Okay, so now that we have sort of a method that works for simple problems, where we already sort of had an idea of what the answer was, let's put that method to use on a more difficult problem. Here, we're going to try a 2D problem. Now remember, for problems that are 2D, meaning not moving along a single straight line, we have to use our equations with arrows instead of numbers. So before, I was able to plug this number in, for example, as simply positive 50. That won't be good enough anymore in a 2D problem. I would have to write this as an arrow with a length of 50 pointing in the direction of north. So keeping that in mind, let's look at this example. So you see an airplane fly overhead moving at 90 meters per second east, but the wind is blowing at 10 meters per second north. What is the airplane's heading and airspeed? Okay, so right away, again, I see there's no boat, there's no river, so I'm going to have to think, what's kind of like the boat, what's kind of like the river? One thing I'll say here is if you actually get this wrong, wrong is in quotation marks there. If you pick an odd object to be the boat and an odd object to be the river, you'll actually still get the right answer. There's no way to actually pick the objects wrong. It's just that there's one sort of choice here that's very intuitive, and other choices, although they work just as well, will be more difficult for you to kind of conceptualize and more difficult to work with. So the thing that I think leads to the simplest choice is, again, thinking, okay, the river flows over the ground and carries the boat on it. So I think in this question, I have sort of the wind or the air flows over the ground, which is where you are, and carries the airplane on it. So the airplane is my boat, the wind is my river, and you are on the ground. Okay, so now let's write down what we know and what we're looking for. Velocity of airplane to wind. Velocity of wind to ground. And velocity of airplane to ground. So let's walk through the question again. And every time we come across some information, let's decide where it fits. So you see the airplane moving at 90 meters per second east. So that's the velocity with respect to you. And you're on the ground. So the velocity of the airplane, as viewed from the ground, is going to be that 90 east. One thing I want to kind of note here, this is a bit of an aside. In both of these examples, I've given you meters per second as the unit. That's convenient because that's our metric base unit for velocity. And if I gave you the velocity in some other unit, you'd probably be tempted to just switch it right away to meters per second anyways. But with this formula, it doesn't actually matter what units we use. Because everything in this formula is just a velocity, we can use any unit for velocity we want, as long as we use the same unit in all three places. So if I want to use meters per second here, that's fine. I just have to use it here and here as well. If I want to use kilometers per hour here, that's fine. I just have to use it here and here as well. If I want to use something ridiculous like millimeters per year here, that's fine. I can do that. I just have to use the same unit there and there. Because all we're doing is adding two things to get to a third. So keep that in mind for when you start solving problems on your own. You can use this formula with any units. They don't have to be metric base units. So diving back into the problem, it says the wind is going at 10 meters per second north. So that's going to be down here for velocity of the wind. And then it says, what is the airplane's heading and airspeed? Remember, this term heading is a hint. We're talking about that very first term in the formula, the one that's not measured with respect to ground. So that's this guy over here. You want to think of this heading as the direction the airplane is pointing or the direction the airplane is aiming, not necessarily the direction it's going to be going in if viewed from the ground. So when it says we want to know the heading, which is the direction of this guy, and the airspeed, speed relative to the air, well, that's the speed of the plane as viewed from the wind or the air. We're basically just asking for the magnitude and the direction of this term. So we're just trying to find this. The magnitude is called the airspeed. The direction is called the heading. Okay, so to our formula. One way, well, I'll write the formula out here again as we normally do. Velocity of boat to river, so airplane to wind, plus velocity of river to ground, so wind to ground, equals velocity of airplane to ground. Another thing I sometimes like to do, because it helps me sort of organize my thoughts here, since all I'm doing here is adding two things together to get a third, I can write that out as like a vertical addition problem down here. I can say these top two things are being added together to give me this third one. So these two ways of writing the formula are both totally fine. And if you like one way a little better, feel free to do that. Okay, so let's kind of plug these numbers in. Velocity of air to wind, I still don't know what that is. That's my unknown. Velocity of wind to ground, well, that's 10 north. And velocity of air to ground, that's 90 east. Remember, I'm not just saying positive 10 for north or positive 90 for east. Because this is a 2D problem, I need to write those directions, north and east. And what I'm going to do now is get to drawing actual vectors. Now, what you could do at this point is you could say, well, I want to isolate this. So I'm going to take this guy, move it to the other side. So I'll get 90 east minus 10 north. And then you could say, well, subtracting 10 north is the same as adding 10 south. And you go 90 east plus 10 south and you find your answer. That would work. Now, at least it would work for this question. But there are questions we'll get to where you're not just looking for one thing in this equation. So it'll be difficult to solve them by just isolating one thing and moving everything else to the other side. So I'd like to show you a way of thinking about these questions that is sort of more general and more applicable to more situations. And the way I think about it is this. I have two vectors here that are being added. So these guys are head to tail. And if I do add them both, do one and then the other, where I get to is this guy, my resultant, which starts at the beginning of the first vector and ends at the end of the next vector. So I've got two things that are head to tail, and then a resultant that goes from the start to the finish. So drawing that out, I've got this. Let's start with the one I know, 10 north. So maybe let's go to a different color here. Let's do a short line. So there's 10 north. And then I'm going to add to it something. I don't know what it is yet. So that means starting here, pardon me, starting here, I'm going to have a new vector. Maybe it'll go like this, maybe it'll go like this, maybe it'll go like this, maybe it'll go like this. I don't know what this one is, right? It's this guy here, it's my unknown. But I know it's being added, so I know it's going to start here and head off in some direction. What I do know is that the resultant of those two, that goes from the start of the first one to the end of that second one, is 90 east. So I can write that guy down. And now I can see, okay, if I'm taking this vector and adding something to it that gets me to here, it's pretty clear that that something needs to be this. So let's put some numbers in here. There's my 10 north. There's my 90 east. And here's my velocity of airplane with respect to wind. So the 10 north, this guy, plus velocity of airplane to wind. So those guys should be head to tail, as they are here. There's velocity of air to wind. Equals, meaning the resultant from the start of one to the end of the next one is 90 east. And that guy is the guy down there. From start of the first one to the end of the second one. So now, all I have to do is solve for VAW, solve for this side here, which in this case is my hypotenuse. So I can use Pythagoras to find the magnitude, and I can use some trigonometry to find the direction. Let's go ahead and do that. So there, I've used Pythagoras to find the magnitude of that hypotenuse, and I can also use some trig ratios to find the direction. Remember, we always define a vector's direction from its tail. So I'm going to probably want to find this angle here. So I know, if I'm looking at that angle, I know the opposite and the adjacent side. So using tangent is probably going to be useful. Okay. So, pardon the little pause there. I've finally found the velocity of airplane with respect to the wind, which has this as its magnitude and this as its direction. So I'm going to write that down as sort of my final answer. Velocity of airplane with respect to wind is 90.6 meters per second. There's the magnitude, and the direction is 83.7 degrees east of south. And this also, it's worth kind of going back to the question and just thinking, does this make intuitive sense? So there was a plane, and we saw it when we looked up to be moving 90 east, directly east. But that was odd because we knew there was a wind blowing north. So if you're an airplane and you're trying to go east, but you know there's a wind blowing north, you're going to have to compensate for that wind a bit by angling your plane a little bit to the south. And indeed, that's exactly what we see here. The heading of the plane, right, the direction of this guy, is a little bit south to compensate for the push north it's going to get from the wind. So a reminder here that the magnitude we found was basically the air speed, and the direction we found was the heading. So, quick recap. When you're solving a problem like this in 2D, you have to keep the direction words in there. You can't just convert them to plus or minus. You want to figure out what thing is kind of like the boat, what's kind of like the river, what's kind of like the ground. You're going to want to write, of those 3 velocities in our formula, what ones fill in the stuff you know, leave blank the stuff that you don't. And then you're going to plug that stuff into the formula. Again, remembering to use direction words, not just plus and minus. And then the key thing at that point is realizing that this formula, in essence, has 2 vectors that are being added that are head to tail, and then 1 vector that represents the resultant. And you're going to draw that triangle using that information. So 2 vectors that are head to tail, and then 1 vector that is your resultant. Once you've drawn the diagram out, it's usually just a matter of figuring out what sides and what angles you know, what sides and what angles you're trying to find, and trigonometry like Pythagoras, our basic trig ratios, sine, cosine, tangent, or if it's a more difficult problem, sine law and cosine law will help you with solving that, and you can take it from there. As we move on in this course, we'll kind of introduce a few little tricks that can trip you up, to things that make these questions a little bit more more difficult. But we'll introduce those sort of one at a time as we get to them. Thanks for watching the lesson. We'll see you in the next one.